Okay, hello everybody. Welcome to our fourth webinar hosted by IEEE Censors Council Egypt chapter. And we are very honored to have today Professor Deepak with us. Professor Deepak, I cannot pronounce the second name correctly, Professor Deepak. So it's,
Carry on.
sorry, Professor Deepak
It's Uttamchandani.
Uttamchandani. Yes,
Correct.
okay.
That's
He is our IEEE Censor Council President and Emeritus Professor in University of Strathclyde. Professor Deepak is an IEEE Life Fellow, 2024 Keithley Award Laureate, and founder of Strathclyde Center for Microsystems and Photonics, with over 320 publications and leadership roles in IEEE Censors Letters and IET Micro and Nano Letters. His work in photonics sensing has revolutionized healthcare, instrumentation, and nanoscale technology. I'm really honored to have Professor Deepak with us. The webinar title is Towards Sustainable Development, the Role of Photonics-Based Instrumentation and Measurements. Welcome, Professor Deepak. Any questions in the talk, please, you can write it in the chat and or ask it after the talk itself. The floor is yours.
Well, thank you very much. And first of all, it's really a great honor to be here, to be with you, all of you, this evening in Cairo, early evening for me here in Glasgow. But I also want to congratulate the Census Council Egypt chapter for the progress that they have made in a relatively short time. And I'm quite aware of the seminars. I've been invited to attend some of these myself. And it is really good to feel the energy flowing out of your community in Egypt. And all I can do is to hope that this amount of energy and enthusiasm will continue into the future years. So great to see you all so active and passionate about the discipline and about the Census Council. So let me then move on to my to the talk itself. And it is, as you can see on the screen, I hope you can now see my secondary screen here. It's towards sustainable development and the role of photonics-based sensors. I actually added the word sensors just earlier, instrumentation and measurement. And you see, I put a little comment below that. And I've said that photonics here includes optoelectronics and imaging, because photonics is actually quite a wide field, and it includes some of these other topics. And what made me start thinking about this topic was that last year in 2024, I was fortunate enough to be awarded one of IEEE's main recognitions for people working in the field of instrumentation and measurement. And that was the Keithley Award. And this is something I was given by my community and something I'm immensely proud of. And part of that award ceremony required me to do a presentation. And I actually thought about it and I said, what is it that this field of photonics-based sensors, instruments, and measurement, what has this done for society and for the community? And I've been working in this field myself for really right from the start of my career. And I thought this would be a really good time for me to maybe try to understand, how this particular technical field was affecting or impacting the global society. So the way I thought about doing it was to to work with my close friend and co-author, Robert Blue. Robert's at Strathclyde as well, and he has also been very, very active in sensing. You can see from the screen, he has experience and publications in chemical and biomedical sensors, in MEMS, in ferrofluids. We've worked on explosive sensors. We've worked on gas flow sensors. We've worked on laser-generated ultrasound. So Bob is very experienced, and he and I sat down and asked ourselves this very same question that I said a few minutes ago. What has photonics done for society? So the way we chose to address this was by looking and thinking about the Sustainable Development Goals. So I'm sure most of you will know that the UN has a set of goals that they call the SDGs, Sustainable Development Goals. This idea was conceived back in 2015, and they gave themselves something like 15 years until 2030 to target and deliver actions related to these Sustainable Development Goals. And there were actually 17 of these SDGs that were identified. Now, sustainable development, I think we all understand where we are. We need to reduce the adverse impact of human activity on the planet's systems. Because wherever you are in the world, you can see the planet's systems are under immense stress due due in part to human activity. And of course, there are natural events that are also taking place. So that is a part of sustainable development, but they combine that with improved healthcare, better education, reduced inequalities, and generally creating opportunities for all. So these were encompassed in these 17 SDGs, Sustainable Development Goals, okay? And it really matters. I think we all understand it matters. We do not want to compromise the ability of future generations to meet their needs, but we have to make the right choices. We cannot just recklessly go ahead and exploit the planet, exploit the natural world, because this will come back and bite us in a very sharp way. And already looking around the world today, you can see events that are happening, natural events, which 20 years ago would not occur. So this is something we have to be really mindful of. So I turn my attention now to this. When I'm talking about sustainability, I want to now share with you my thoughts about e-waste. E-waste is electronic waste. And in 2022, there was 62 billion kilograms. So that's 62 million metric tons of electronic waste produced. Now, what do you do with e-waste? Well, what happens is, unfortunately, the majority of e-waste just gets dumped. So this graphic here on the right-hand side shows you in the green color, which you can see over here, it tells you what percentage of e-waste is actually processed or recycled in a responsible way, okay? And so you can see in total, less than 25% of e-waste is recycled responsibly or handled responsibly. And if you look at the subcategories, you find that the subcategories are different. So if you have small equipment, this is the amount of recycling. If you have large equipment, then the recycling is maybe a bit larger, and so on. If you look through each of these graphics over here, you see that really, at best, you might be able to reuse 30% of e-waste. But what happens to the rest of it? Well, it goes there. Okay, so this little clip was cut out of my local newspaper. This was not a scientific journal. I cut this out from my local newspaper. Okay, and my newspaper was talking about this whole business of electronic waste. And the part of it that doesn't get recycled formally just gets dumped into what's called an e-waste mountain, okay? And people then are going through these e-waste mountains, trying to recover some of the stuff, trying to recover valuable materials from all of this e-waste. It is dangerous, it is really unhealthy, but for some of the less privileged people in our society, this is perhaps an only option for them to make a living. But it is not a good way to handle our e-waste. So even when you are sitting here as an engineer, think about whatever you design today, you manufacture tomorrow. But what are you going to do with this when you have completed your manufacturing? The device has come to the end of its life. What are you going to do with it? How are you going to handle it? That's a question that we must ask ourselves as engineers. Now, coming back to the SDGs, as I said, there are 17 Sustainable Development Goals, okay, and they're shown on this particular slide over here. And what I intend to do through the remainder of this talk is I'll just go through these 17 goals one by one, and I'm going to demonstrate to you how photonics, instrumentation, measurement, sensors has somehow connected and linked into each of these SDGs, okay? So let's start with number one. So number one is about poverty, or to have no poverty. We are far away from that. So today in our world, we have over 700 million people who live below what's called the poverty line. And the poverty line is defined as if you earn 2.15 US dollars per day, that is the poverty line. And over 700 million people earn less than that every day. And so they're deemed to be in poverty. This lower graphic actually, with this negative trend, this is actually showing that the number of people within the poverty, the number of people considered to be in poverty has been reducing. So society has progressed, okay, because this graph has a negative slope. But there are still a huge number of people who live in very poor conditions. So the question is, how do you sense global poverty? How do you measure it? Because if you want to solve the problem, you want to understand where this problem is arising. And there are many ways that people look about measuring poverty, understanding poverty. You can actually do detailed surveys of the population of your country, of your region. You can send out surveyors to walk around the country, meet people, and form an assessment. But there is a way the technology comes in, and it comes in through what is known as nighttime light imagery, NTL imagery, okay? And this graphic here shows you what NTL imagery is. It's just showing you, it's a satellite image of the world. It's, well, not of the world here, it's actually showing you Europe and Africa. And the lights over here are, of course, centers of population. And so this is where people are accumulating. And by using nightlight imagery and connecting it to various other algorithms, it is actually possible to make a deduction about the state of poverty in different parts of the world, in different parts of our planet. Okay, so I'm not going to go into the details. There's a references at the bottom over here, and you can maybe pick up the details from there. But the point I wanted to say is that these are satellite images, these are remote sensing instruments, and photonics and optoelectronics are key equipment within this type of equipment, within these kind of sensors. So let's then move on to the example of zero hunger. Okay, and this is about food production, and what we want to do is to be able to produce food in a sustainable manner that does not adversely affect the environment. And there are different ways of doing it, and this is one example of how photonics is applied in agriculture. So this graphic is showing you a drone, and this drone has with it a hyperspectral camera. So hyperspectral cameras actually image over a wide range of wavelengths beyond the human eye's visibility. So so in this particular example, the camera images from 400 nanometers, which is just in the blue part of the spectrum, all the way up to 2500 nanometers, which is way into the infrared. Okay. And what you can do with these images is you can use the drones to survey an area, and by capturing these hyperspectral images, you can review these images, and these can give you benefits in the area in the form of increased yields, reduced usage of resources, for example, fertilizer, early detection of plant diseases, monitoring the use of water, and so on. So there's a great deal of information that can be gathered through these types of imaging sensors, which again are based around photonics. And this idea has gone even further. It has gone into space. So for example, this is showing the EOS sat, which is a satellite manufactured or produced in South Africa. And the purpose of the satellite is to scan the planet from much higher than a drone can scan, but again, for the same generic purpose, to be able to scan and image agricultural areas around the world. And by using these hyperspectral images, you can actually start making important conclusions about what is future yield, if there is disease, if there are some areas which are in drought, and so on and so on. Okay, so this type of satellite technology, again, built around photonic imagery, is an important tool. This slide over here talks about moving from land to water. So I'm talking about aquaculture over here. And I'm particularly thinking, for example, of fish farming, because many parts of the world, many people are rely on fishing and fish farming for their livelihood. Now, fish farming can actually be damaged if ammonia enters into the environment. And ammonia is a chemical that enters the environment quite easily through municipal waste discharges, through animal discharges, through agricultural fertilizer discharges. All these discharges push ammonia into the water environment, okay? And this is extremely damaging for fish and for fish farming, okay? And so the important thing is to be able to monitor a pool of water, a body of water where the fish are being farmed, and make sure that these damaging chemicals like ammonia are kept out of the system, or you at least are aware that they are in the system. And so this again requires the use of a fiber optic sensor. I'm not going to go into the details, there's no time, but essentially this device is a sensor, and this sensor gives responses to ammonia concentration in the region, in the 200 parts per billion region, which is when it becomes around when it becomes problematic. And this graph shows that this sensor operates both in freshwater and in saltwater environment. So this kind of sensor could be useful to a small fish farm to make sure that the quality of their water is to the right standard. Okay, so that was that. Let's move on to number 3, good health and well-being. So I'm sure you will all be aware that laser technology has made many impacts on our health and well-being. But let's look at 1 or 2 examples. Here's one example with biomedical screening. This is work that was done actually just 4 or 5 years ago. And here what the goal is to detect respiratory viruses. The samples of human fluids are collected. They're dropped into this chip, this multi-purpose chip over here. DNA is amplified, and then fluorescence is used to detect the DNA, which then signals the presence of the viruses. So the important point I wanted to share with you with this particular slide is that all of this is done with a cell phone. This is not done in some complex university laboratory or anything like that. What has been done is that a standard cell phone has been used. The camera of the cell phone is used as the image sensor to measure the colors. There are various optical filters inserted into this little device, okay? But the point is that this device has the capability. It's a mobile device. You just connect the sensor chip to the cell phone, make a small alignment, and you have in your pocket a laboratory that can detect the viruses, and you can take this with you wherever you go. Isn't that amazing? And so that's just one example, and I don't have time to go through so many. This is just one example of how viruses can be detected very, very simply. Education. Let's move on to education. I think what I should say to you that in most of these examples, I only have time to give you like one or two examples. Otherwise, we could discuss so many examples. This is just showing you one or two examples. So with education, this idea of immersive learning, I think many of you will have at least seen pictures of this. If you've not experienced it yourself, you get head-mounted displays. Head-mounted displays have a lot of optoelectronic technology built into them for them to function. And head-mounted displays can be used for so many different applications, all connected with education, improving people's knowledge. They can be used in transferring medical knowledge from one part of the world to the other. So you have a group of physicians, surgeons, everyone is wearing their head-mounted display, and using virtual reality, you can look at the patients, you can watch how operations are being carried out, and so on. So all this happens with the help of photonics, because the displays that go inside these head-mounted HMDs actually require photonic materials, quantum materials, to get really, really high quality, very, very bright displays. So this is one example of how education benefits, whether it's medical education or the previous slide about education for young people, even at schools. Gender equality. This was very interesting, and we had to think hard about how we could pull this topic into the scope of this talk. And we did it in a quite interesting way. And I was very surprised when we did the research on this. I did not know that, generally speaking, in the population of the world as a whole, women tend to suffer more with eyesight problems compared to men. Okay. The actual figure is that 55 eyesight problems with eyesight and loss of vision affects 55% of women compared to around 45% of men. Now, I myself cannot comment on the biological reason for this. There will be perhaps there may be biological reasons that this is the case. There might be other reasons which I'm not qualified to understand that could be behind this information, that could be behind this pattern. But this pattern is there. Women compared to men suffer more when it comes to eyesight. And this is a problem, because you could say that if the problem is known, why can't we solve it? But actually, because of cultural issues, because of societal issues, these problems are not solved easily. You know, if you're trying to treat the patient, there are costs that are incurred. You may have to travel. If you're living in a small community, you may have to travel to the nearest big town to benefit from treatment. There's a difference in perception about the value. I'm sorry to say this, but this is something I think we may all recognize ourselves. There's a global difference in perception about the value of supporting and treating women compared to men. There's lack of access to information, and all of these things are there. And we have a responsibility to try to equate this, because now it is an inequality. Here on the right-hand side, is our first steps from my own university, the University of Strathclyde, to address this issue. And what was done a few years ago was that we created what's called a phone-based ophthalmoscope. So an ophthalmoscope is the device that when you are when you are living in a city, you go to your optician and you have your eyes tested, and they take a photograph of the back of your eyes, because from these photographs, they can actually make some conclusions about your health. Okay? This piece of equipment is actually a major piece of equipment costing many thousands of dollars. But actually, you can transform this quite easily into a mobile phone by adding a few extra purpose-designed components. And we have done that in our university, in our biomedical engineering department. And there are two pictures over here. They're both of the retina of an eye. This picture on the right that I'm showing you was taken by a professional equipment. This picture on the left was taken by a smartphone-based equipment. So again, a smartphone has optoelectronic devices in it. And then you need to have some extra bits of equipment, lenses, and so on to focus the light. So all of these photonics kind of come together to be able to allow you to be able to measure and record, not measure, to record the retina of patients. And now the medical practitioner can go to the community. You don't have to travel from the community to the practitioner. So when I mean medical practitioner, I mean the optometrist, the person who does the eye test. And I hope that this way, perhaps it allows a more equalization, that when women cannot travel to these distances, then maybe people come to the small communities and can assess everyone on the same basis. Now, once you know someone's eyes, someone has medical needs some medical attention, maybe even needs glasses. Well, how do you actually get the prescription? Well, those of us who live in big towns, it's easy. I fix an appointment with my optometrist. He puts his equipment in front of my eyes and he tells me, Deepak, yeah, this is your prescription. 3.1, whatever the numbers are. But the question is, not everyone has the opportunity to do that. So this equipment over here, it looks like just a pair of binoculars, and it is a handheld device. And the purpose of this device is to be able to put it against the face of an individual, and the system itself internally sends in a light beam into the eye, follows and tracks the light beam as it comes back out of the eye, reflected from the back of the eye. And by following the trajectory, it is possible to actually work out what is the power of the lens of the person who's been tested, and you can actually get a basic prescription. And even if that prescription is not perfect, it is much, much better than at having at least some basic prescription than having no prescription at all, or having to travel for hours or a day to reach somewhere where your eyes can be tested. What is a natural goal from this? If you can get a prescription, then my dream is, can someone make 3D printed glasses? Can I take my 3D printer, I take this piece of equipment, I test someone's eyes, I say, okay, I know the prescription, I feed that prescription into a 3D printer, and it produces the basic eyeglasses for that patient. We haven't reached that stage yet. I think the materials technology has the capability to do it. I think this is doable and maybe something that people should think about. So we're still talking about the gender issue, about women. And here I wanted to point out to you that my own society, IEEE Photonics Society, has women in photonics programs. SPIE and other societies like Optica, all these professional societies devote effort and time to supporting women in this particular discipline. And this is something particularly to be noted, that here is a volunteer in Iran, okay, who has got a group of schoolgirls with her, and she's just doing some very basic optics, just using light emitting diodes, using some simple lenses, concave lenses, convex lenses, and just doing very, very simple experiments of physics. But what I want to show you here is that this is led by a woman volunteer who is supporting her class of female young people who maybe one day will go on to become photonic engineers themselves. Okay, let's move on. 6, clean water and sanitation. So I think we all understand why clean water and sanitation is important for humans. Okay, how does photonics help us? There are many different ways. This is just a few examples. There are many examples. Here, the technology here is trying to detect arsenic in drinking water. So arsenic is an element which is bad for humans. If you absorb it into your body, it's obviously not good for your health. And even small quantities of arsenic can do quite a lot of damage. So here, this technology is a photonics-based technology. It's called surface enhanced Raman scattering. So you take a small sample of the water, you combine it with what are called nanocolloidal materials, and these form complexes, and these complexes flow through this optical chip. And by using a particular kind of testing equipment, Raman testing equipment, you are able to measure right down to parts per billion concentration, which is very, very high sensitivity, but it's needed if you want to keep the water safe. Here's another technology. It's SPR, stands for surface plasmon resonance. This is something I did many years ago myself. And this is trying to detect heavy metals in water, okay? And this graph that you can see on the bottom side over here, this is just a graph that is changing as the concentration of lead in water changes. So many of you may know that lead enters into the water supply. Again, it is bad for human health, okay? And the measurement is important, and really photonics is really the best way to make these measurements cheaply and rapidly, okay? And this is an example of how this particular technology is applied to detecting lead in water. Okay, let's move on. Item 7, affordable and clean energy. At least let's look at the clean energy. And I show you these two graphics over here, and both of these graphics are related to wind energy, and they're all wind turbines. So here you can see a wind turbine, and what is installed is LiDAR, which is laser radar. The laser radar looks forward, it measures the wind speed, it measures the wind direction, and with this information, the algorithms are available to adjust the parameters and angles of these turbines to get maximum efficiency out of these turbines, okay? And actually to also keep them mechanically safe. Here on this side of here, this lower graphic is again showing you a wind turbine, but this time I'm looking at the blade of the turbine and the tower of the turbine. And what is happening in both cases, that within the blade and within the tower, there are fiber optic sensors that are embedded. And the purpose of these sensors is to measure strain, to measure temperature, to measure curvature of the blades. And having all these factors available to us makes sure that these wind turbines have the maximum life, they have the maximum efficiency as well. So we are using photonics technology to extract the maximum life and maximum performance out of these types of turbines. Okay, let's move on. So those were just two examples around renewable energy. So item 8 is about decent work and economic growth. And I have different slides for that. So decent work, this graphics perhaps is not so clear, but I wanted perhaps you to take in the message. This technology here is about worker safety. And here, the purpose of this technology is to detect gases. So this is a gas sensing equipment, and it's there to detect leaks from gases that could be dangerous, okay? So if there are people working in various sectors of energy, they're working in oil platforms, they're working with handling gases and so on. If you have leaks, obviously there's risk of explosion, there's risk, this is very hazardous. So there are various technologies here. This is based on fiber optic and photonics technology. And these technologies are almost intrinsically safe. You can put them into quite dangerous environments, but they do not, they are still very, very immune to the environment itself. And they provide very reliable measurement about about gas concentrations. And so this type of data can then be used to support the safety of workers who go into some of these dangerous areas. That was about the worker safety. Here, I wanted to talk about economic impact because this is what this SDG is looking at. And I just want to share with you how important photonics is around the world. And this graphic is really quite interesting. So back in 2021, the global total economic impact of photonics was in the region of $2 trillion, okay? And it gets broken into these subcategories. So you have consumer photonics, okay? This, for example, includes fiber optics coming to your home, delivering bandwidth and internet to your house. Well, okay, that's also that, I guess, is embedded with communications. There's in advanced manufacturing, lighting, displays, solar, biomedical, defense. All of these sectors rely heavily on photonics technology in one way or another, and photonics makes a huge contribution to the global economy and gives opportunities around the world. Small companies, medium companies, large companies can benefit from this very high amount of funding that is around the world. So let's move on to item number 9, industry and infrastructure. Okay, industry, innovation, and infrastructure, but I'll concentrate on industry and infrastructure. So for industry and so for infrastructure here, I want to direct your attention to this structure here. This is just showing you a bridge, but this bridge actually has got fiber optics which are embedded within the structure of the bridge. And the purpose of the fiber optic there is to monitor the bridge, to continuously monitor the temperature with something like 1 centimeter resolution, to monitor the temperature of the bridge, to monitor the strain of the bridge. And so this is an infrastructure which is being kept, whose life is monitored, whose performance is monitored, whose life is extended by incorporating fiber optics to monitor the mechanics of that structure. Down here is just one example of how lasers and photonics are used in manufacturing. So lasers themselves are used, for example, in welding, but there are other applications of lasers and cameras where you want to have the robotic welding, and the camera and the lasers are focusing on the object, and this focusing creates a 3D kind of replica of the object. And from there, the robotic welder comes in and starts welding different parts. So this is a high degree of automation in the welding area, for example, using lasers, using CCD imaging cameras, and combining both of them. Okay. Reduced inequality. So how can we help to reduce inequalities? Can we do that? Yes, we can. So here is an example which is health related. And in this graphic over here, what you're seeing, these blue objects you see over here are 3D printed microscopes, okay? Microscopes are important because if you are a laboratory technician and you take a blood sample from somebody, you can actually send, normally in the Western society, those blood samples are sent to the lab, they're viewed under the microscope, and some assessment is done. But a microscope is actually quite an expensive piece of equipment. Even basic microscopes can be quite expensive. So here the idea was to use the simplest off-the-shelf components, lenses, imaging devices, filters, optical filters, and using 3D printing to actually create structures like these blue structures over here. And you can see that behind this medical technician, there is the screen, and this screen is showing you what looks like blood cells. So here, this very basic microscope has been used by this medical technician somewhere in a less privileged part of the world, and yet this person, this medical technician, can make some important initial conclusions about any patient by having this type of technology available to him. So this is beginning to help equalizing. Instead of having a high state-of-the-art microscope, you can actually have a fairly simple device that works just as well. Sustainable cities, sustainable communities. This is SDG number 11. And what I wanted to share with you is looking at the cities first. Many of you are aware of how driverless cars are beginning to enter into our cities. There are other technologies that you see. This example here on the top right is a smart street light, and this street light is monitoring what's happening around it. If it gets too dark, it will turn on. If somebody is walking, it can sense that someone is walking and it may turn on, or it may get brighter. So there's a lot of things that you can do with smart street lights, which just involve some basic imaging, some basic sensing. Again, photonic-based sensing and imaging contributes to this area. And then down here, the bottom left over here, I'm just showing you a car which has laser radar on it. So there's radar on the roof, there's radar on the front. And these technologies, together with other types of technologies, are the direction that will lead us towards driverless cars. And you can imagine the cities with driverless cars, so you don't have crazy traffic jams where you have thousands of cars trying to get stuck in one part of the city. With this type of driverless technology, you take the human out of it and the machine does the job. And sometimes I think we can all agree that machines do jobs better than humans can do it. So this is a way forward towards smart cities, less congestion on the road by using, say, driverless vehicles or automatically driving vehicles where the human driver is not involved. But to do that, you need these types of scanning technologies. Here's another example. Here, once again, I'm showing you a drone. Okay, so this is showing you a standard drone. But this drone is carrying this device over here, which is a laser spectroscopic equipment, which is used for monitoring greenhouse gases. So put it this way, the bottom two slides showed the laser-based equipment. There's lasers, fiber optics, all in here, but these equipment are now connected to the drone, and the drone flies above an area, and you can look down this area. It may be an urban area, it may be a rural area. These experiments were done by some of my friends in India, and they were trying to detect CO2. CO2 is a greenhouse gas, as you all know. So monitoring it is an important thing towards future sustainability. We talked about, let me go back one. Yeah, we talked about also resilience. This upper diagram shows you what happens when a tsunami can come and hit the shore. It creates loss of life, huge loss to property. Property, I suppose you can in some way adjust to, but when you have loss of life, obviously that is not that's not a situation that can be reversed. So there are fiber optic technologies now sitting that are being developed for the bottom of the ocean. And when earthquakes happen in the sea and tsunamis go, as the tsunami travels along the ocean, there are various sensors. The pressure changes on the ocean floor, and the fiber optic sensors are sitting there along the ocean floor, just monitoring these pressure changes, feeding it forward to the monitoring stations, which then give out the appropriate warnings. Okay, so let's look at this responsible consumption and production. Here, I'm looking at food. So let's imagine we are producing food, and you know how much food gets wasted because sometimes we don't handle the food we produce in a careful and responsible way, and there's so much wastage. So here, for example, the idea, what's happening here is that this is a hyperspectral camera. It's looking at these different, in this case, they look like apples to me. And you can remember, we are seeing it in the visible, but the hyperspectral camera looks at it beyond the visible wavelength. So it sees things that our eyes cannot see. And it can detect damage in fruit and vegetable. It can see which ones are beginning to get ready to go off the shelf. So which ones are very, very fresh, which ones are maybe not so fresh. You can use this technology to select this out and make sure that you still manage to use the food items which are just not 100% fresh. They're just coming to the limit of that instead of just throwing it away. Why throw it away if you can reuse? If you can use it and you're still safe to use it, and the technology to help you to reduce that food waste is actually viable and available. So on climate action, let me look at what we have over here. Okay, this is actually some work we are doing in my own university, in our own laboratories. But this particular graphic shows you what is happening in one of the laboratories of our partners. So this white disk actually is a jet engine. And what we're trying to address is the problem that we all understand, that emissions from jet engines are harmful to the environment. I think we all know that, okay? The question is, what can you do about it? Well, before you can solve that problem, you need to have a better understanding of the exact composition of the emissions that come out of a jet engine, okay? And although people have a general idea of what those emissions are, there are still room for improved measurements to get more accurate information of how those emissions are distributed in the back of a jet engine, because by understanding that, you can actually improve the design of the jet engine and reduce these harmful emissions. Okay, so this size, you can imagine this height over here is something like 30 meters high. Okay, there's a jet engine sitting here, and behind this, which you absolutely will not be able to see, are fiber optic sensors. And these fiber optic sensors are positioned behind the engine. And when the engine is then turned on, the emissions are monitored by using this technology. It is an amazing technology. And I have to say, I'm saying it, of course, my university, my colleagues are part of this. So I'm smiling. I'm so proud of them. Okay. But this is an amazing technology found nowhere else in the world. You have to come to Glasgow in Scotland if you want to see this. Okay. So this is how this technology is trying to look at the emissions from jet engines. Okay. And similarly, you can look at emissions from marine, from vessels. And I think some of you may know that ships are also damaging to the environment. The engines from the ships produce emissions, and there are stricter and stricter regulations about what ships are allowed to emit. But you still have to find a way to monitor them. And here there are technologies that use photonics, that use spectroscopy, light scattering, and so on, to be able to monitor oxides of nitrogen, oxides of sulfur. These get emitted by the ships, and there are strict regulations as to how much can be emitted. And these technologies are here that can be able to monitor these emissions and make sure that people don't misbehave. Okay. Life below water. Life below water is in our oceans. Our oceans we have treated like a dump. We should be ashamed of how we treat our oceans. The acidity of oceans has increased by 30% just over the period of about 150 years. Okay, and we rely on the oceans, but we treat it with so much disrespect. We treat the marine ecosystem recklessly. And I'm not telling you something that you don't already know. I'm just telling you something that many people have said before me. And so we have technologies here, fiber optic monitoring technologies, to understand what's happening in our oceans. So this particular sensor, this device, this is an instrument which measures oxygen, dissolved oxygen in the ocean, it measures pH, so acidity, and it also measures temperature. So three measurans, three quantities are being monitored here on the floor. It's important to collect this data, gather it, and make sense of it, but in the long term to try to reverse the decline in the health of our oceans, because we rely, as a human race, we rely so much on the oceans. And there are other things we find in the ocean. I think many of you will know microplastics are in fresh water. So from the rivers, from the lakes to the rivers to the oceans, plastics are also damaging. Microplastics, they enter into the ecosystem, they enter into fish. Humans eat the fish, they enter into our bodies, and people have discovered in the human reproductive system, microplastics are existing. They affect fertility, they are damaging. And there are technologies here, photonics-based technologies. You have microplastics here, you're using lasers and detectors to get light scattering from the surface of water. And by looking at these speckle diagrams from the scatter, you are able to make some deduction about the concentration of microplastics in the oceans or in any body of water. So that is something that photonics, has been able to contribute. And then life on land. Well, here I came across this very interesting example about measuring insects. So, many of us think insects are perhaps annoying, but insects actually have a very essential role to play in nature. They are part of the whole ecosystem, and they make sure that pollination takes place. They eat some of the parasites that affect our crops. But insects themselves are under threat, okay? Because we are using more and more fertilizers, and these things begin to damage the insects. And so the concentration and abundance of insects, which are so important, is reducing. So this technology here is actually a photonics-based radar, and it's actually trying to monitor the concentration of insects remotely from maybe a few hundred meters away. Okay, so as the insect flies around, its wings are vibrating, and that affects the laser beam that is being directed towards them. And when that laser beam is detected, you can make some conclusion about the concentration of those insects. And this lower graphic just shows you what happens. You can see that in the midday at 12 o'clock, the concentration of insects is low, but as we get towards evening, 9 p.m. in the evening, the concentration of these insects is increasing. So a lot of them are active in the night time. But really what I'm trying to demonstrate to you is that there is a photonics technology that can monitor the concentration of insects. It's important to keep insects. It's important to make sure insects remain as part of our ecosystem. And then coming to peace, justice, and strong institutions, here I'm showing you that photonics can be used for detecting illegal drugs. For example, these are amphetamines. Amphetamines, if you consume amphetamines, they actually go through the system, they enter into your sweat. And there are sensors over here that you can put, as you can see over here, you can put a patch onto the skin. This patch picks up the sweat of the individual, and then you can use this instrumentation here, again using Raman as a methodology, and you can use this instrument to monitor this patch, and then this tells you whether a particular patch has got these illegal drugs or not. And on the same theme of illegal drugs, this is just another technology. You have a sample over here. You're again using spectroscopy. So you have a light source. Up here, you have a sample that you're testing, okay? And you can look at you can actually work out the composition of these samples using this fiber optics-based device instrument, okay? And you can work out, if you have illegal drugs and so on in the system. And then finally, partnership for goals. So I just want to show to you that photonics is everywhere. Okay, so photonics is a partner of SDGs. Okay, and whereas the 20th century was you could say was the century of the electron. Certainly this century is the century of the photon. And there's a lot of work happening. Some of those examples I've shown you in terms of these groupings of people. In my own country here in the UK, we have UKRI, which is the body that distributes research. And there's a whole amount of photonics. There's a whole amount of money invested in photonics for environment and sustainability. So this is scaling up the effort. This is the Photonics European Hub. And once again, this is scaling up across Europe. But again, this European hub is focusing on climate change, on green energy, and so on. Okay. And there are other bodies that this is a part of the IEEE. This is another part of IEEE. It's SUSTEC. It's a Sustainable Technology Conference. And the photonics community also supports this conference. So community building is also an SDG. So let me share with you my final thoughts. It's 1 minute past the hour. I think we may have 5 minutes or 6 minutes left. Let me just share with you my final thought. That first of all, as engineers and applied scientists, we are intellectually and practically well equipped to contribute to the SDGs. We are trained to do this. We may not think about it, but we are actually trained. And particularly the discipline of instrumentation measurement has already played a major role in developing these new technologies which contribute to the SDGs. And over the past 50 minutes or so, I've just given you some examples, but as I said to you, there are more examples than I have time to give you. So instrumentation and measurement in general contributes, but the subset of that's what I've been talking about for the last 45, 50 minutes, the sub-discipline of photonic instrumentations and measurement. That's what we've been reviewing in the past 45, 50 minutes, okay? So, as I said, there are many examples of photonics instrumentation and measurements, which I haven't had time to include, but there's so many different variations and possibilities. So, as academics, as budding engineers, as professional engineers, we should keep motivating our students. Really important. Keep the students motivated, the young engineers motivated to think about the sustainability, to think about circularity. You know, I did not even mention the circular economy, circular manufacturing. That is another topic. But this topic around sustainability, about circularity, about reusing, we have to think very much along these directions. And as engineers with an interest in instrumentation and measurements, we have a very crucial role to play. Finally, before I sign off, I just have a little bit of advertising to do. Today is the 13th of August. So in 2 days, 15th of August, the IEEE elections are taking place for a particular position. It's the position of Division X Director. Those of you who are qualified to vote, I hope you will consider giving me your vote. So with that, everyone, I thank you for your attention. I hope this has given you at least some insight, but it has given you something to also think about as you develop in your own careers. Okay, I hand back to the leadership.
Thank you, Professor Deepak, for this enlightening talk. And if anyone have any question or need to comment or anything that was mentioned in this talk, please go ahead. Okay, I have one question. Yes, Dr. Sameh, please. Okay. Thank you for such an interesting talk. I have one question, actually. If you can comment on, there are 17 SDGs. In your opinion, which one of them or couple of them that photonics-based instrumentation and measurements contribute heavily in these?
Sure. I think that I hope this is an answer which everyone would agree with. I have seen for many years this whole piece of monitoring water, whether it's monitoring drinking water, as I gave you an example, whether it's monitoring the ocean. The photonics gives you, this type of technology gives you some of the most accurate data about that kind of monitoring. Okay, so measuring concentrations, measuring chemicals are important. So linked to that too, if you talk about about human workers, and we send human beings to go into risky areas to do something for us. There are times when you have gas leaks and explosions, and actually there's really no reliable alternative technology apart from photonics that can address some of those goals as well. Okay, so those are the two that kind of jump straight to my mind. But also the thing about the climate change, the impact, for example, of emissions from airlines. If we are realistic, we have to accept that at least for the next 15, 20 years, emissions from from aircraft will continue because there's no alternative. I want to go and see my family somewhere in the world. I get on a plane and that plane will emit, right? But a great deal of work is being done in trying to control those emissions, reduce the harmful effects of those emissions. And there is absolutely no competing technology that can monitor these types of emissions that affect the upper parts of the Earth's atmosphere, where some of these gases are emitted, the heights where planes will fly. So those are just like three examples where I would say the competing technologies, maybe the competing technologies are not in terms of pricing or in terms of sensitivity. I think photonics has a great step ahead, has a great advantage there.
Okay. Thank you. Thank you very much, Professor Deepak. Thank you. Each one attended this interesting webinar, and looking forward to more webinars. Thank you.
Thank you for inviting me. And as I said, once again, great progress from the Egypt chapter of the Council. Looking forward to just tracking what you guys are up to, and I can see great progress has been made in a short time.
Thank you. Thank you very much. Much appreciated this recognition. Thank you.
Very welcome. Okay, bye bye for now.
Bye bye.